Hi everyone, my name is Ralf and I'm a PhD student at the Learning Systems and Robotics Lab, TU Munich, advised by Professor Schoellig. I'm happy to present our work, Is Data All That Matters? The Role of Control Frequency for Learning-Based Sample Data Control of Uncertain Systems. Machine learning has become very popular in control. It's often used to learn a dynamics model from data, based on which a controller, potentially a robust controller, can be designed. However, data collected from the system can never fully eliminate uncertainty about the system's dynamic behavior. Therefore, we still need feedback to ensure stability and closed-loop performance. In digital control systems, feedback is usually applied at a certain frequency, the control frequency Fc. This design parameter is rarely considered, but we show that it actually plays a very important role when controlling uncertain systems. Specifically, our motivation for this work was to investigate several questions regarding the control frequency. What impact does it have, also compared to the amount of data? So what impact does compensating for uncertainty via fast feedback have compared to reducing uncertainty via collecting more data? Also, we're wondering which control frequency is actually required to control an uncertain system, and more general, how can we use the control frequency, which is usually fixed in control engineering, use as a design parameter and leverage the additional degree of freedom that it provides in the controller design. How can we approach these questions? If we take a discrete time perspective, then we obtain a dynamics model that's specific to a fixed sampling time, and we cannot just arbitrarily vary the control frequency for this model. In continuous time, the model is not specific to a fixed sampling time, but we also do not even have a notion of control frequency here. So we asked ourselves, how can we vary the control frequency without changing the model? Or a little more concrete, how can we design a discrete time controller for an uncertain continuous time system? For this, we developed a framework that combines probabilistic model learning and robust sample data control. Why? Because this framework allows us to control an uncertain system at different control frequencies without having to relearn the model. Because of this, we can vary the control frequency and study its impact, and also the trade-off between control frequency and data or model uncertainty. Before presenting our approach in more detail, I briefly want to introduce sample data systems. We obtain such a system by combining continuous time dynamics with a discrete time controller. The common stability conditions for LTI systems do not hold here because of the TK that we have here. One approach for analyzing the stability of such systems is based on rewriting them as a system with a time-varying delay, tau of t. We can assume that this delay has an upper bound, which is usually given by 1 over the control frequency. Then stability can be analyzed using, for example, Lyapunov-Krasovsky functionals like the one that is shown here. This has been used to derive sufficient stability matrix inequality conditions for stability in the nominal case where A and B are known. In our work, we assume that A and B are learned from data and subject to some uncertainty as a result of estimating them. And we then derive stability conditions for that case. And I'll talk about this a bit later. Let's formalize our considered problem. We consider a partially known continuous time system from which we have collected noisy observations. We want to robustly stabilize the system with a discrete time controller and study the impact of the control frequency at which this controller operates. We're also interested in the minimum control frequency at which we need to apply feedback to the system such that robust stability is guaranteed. Our problem can be decomposed into 3 subproblems. We want to learn a local linear approximation g hat of the unknown component of the dynamics from the observed data. Based on g hat and the associated uncertainty, we want to compute the minimum control frequency and also a stabilizing controller that is guaranteed to stabilize the system at this minimum frequency. Lastly, we also want to be able to optimize the control performance for a certain control frequency so that we are also able to analyze the impact of the control frequency not only on stability but also on performance. First, I'll briefly explain the probabilistic model learning component of our framework. We want to learn the linearization of the system about an equilibrium. For this, we use Gaussian process regression and assume that the components of G, so the unknown dynamics, are drawn from Gaussian processes. We use the squared exponential kernel here for the GP, but we could also use other differentiable kernels. We then learn a GP model via standard log likelihood maximization, and then we linearize this GP model around the equilibrium. For this, we use the fact that the linearization, that the derivative of a Gaussian process is again a Gaussian process. In that way, we then obtain an uncertain linearized system of the dynamics. Eventually, we want to control this uncertain system with a sampled data controller. However, existing stability conditions do not consider the model uncertainty that we have in these linearized dynamics. To address this problem, we rewrite the system or the uncertainty, so these element-wise products, as matrix products, where all matrices except from delta are known. And we will see this rewritten uncertain linearized system again in a second. Now let's get to the main aspect of the paper, which is designing a robust sample data controller for this learned uncertain system that can operate at different control frequencies. Combining the continuous time dynamics model that we just saw with a discrete time controller gives an uncertain learned sample data system. Now, under which conditions is this system stable? We derived sufficient robust stability conditions for this uncertain linearized system as matrix inequalities. These matrix inequalities are quite large, and I don't want to get into detail here, but the main point I want to highlight is that we can actually see from this theoretical result that stability depends on both the control frequency and model uncertainty. In addition to checking whether the system is stable, we also want to calculate the minimum control frequency that is needed to be able to stabilize the system. For this, we need to formulate an optimization problem that involves these stability conditions as constraints. Unfortunately, the matrix inequalities are nonlinear because we have products between the scalar decision variables epsilon1 and epsilon2 and some of the matrices. However, in our paper, we show that we can actually eliminate one of these scalar variables without sacrificing optimality. The idea of the proof is shown here on the right. We show that the set of optimal solutions in the epsilon1, epsilon2 plane is a line that goes through the origin. And as a consequence, we can restrict ourselves and to optimize only over the red curve here instead of over the whole 2D plane, and we're still guaranteed to find the optimal solution. As a consequence, we can calculate the minimum control frequency required to be able to stabilize the system by solving this generalized eigenvalue problem. And this is a special form of a semi-definite program if we fix epsilon, and yeah, this can be solved quite efficiently. Solving this yields the minimum control frequency and also a stabilizing control gain that's guaranteed to stabilize the linearized system at the computed minimum control frequency. However, this controller can be quite conservative because it only considers stability, and it's therefore unsuitable to analyze the system performance at different control frequencies. So we also investigated optimizing the control performance for learning-based sample data control. We want to minimize a quadratic cost, which is, however, non-trivial for sample data systems. Therefore, we made an assumption and considered minimizing an upper bound on J instead. This allowed us to formulate a second optimization problem. If we solve this, we obtain an optimized control gain for a fixed control frequency. Now, what have we gained from all of this? We have developed a method that allows us to robustly control an uncertain learned continuous time system at a desired control frequency. We can now use this to investigate the impact of the control frequency and also compare its role to the amount of data or the model uncertainty. In our evaluation, we simulated a nonlinear 2D quadrotor system with 6 states and 2 inputs. Here you can see the minimum control frequency obtained by solving the first semi-definite program. We can see that if we have less data about the system, or if the noise in the observation increases, then we must control the system at a higher frequency. Also, in these cases, we are less likely to even be able to compute a stabilizing controller for any control frequency. Now let's look at the control performance. If we have 200 data points, we need to run the controller at least at 25 Hz. Increasing the control frequency greatly improves the performance, as shown by a faster convergence of the system to the set point. For 600 data points, we can observe the same pattern. However, we can also see that in this case, running the controller at 22 Hz gives much faster convergence to the set point than running the controller obtained using 200 data points at 25 Hz. We wanted to investigate this trade-off between the amount of data and the control frequency in more detail and calculate the cost function for many different pairs of number of data points and control frequency. We observed that the control frequency has a very strong effect on the amount of data that's required for stability or achieving a certain performance. An increase in the control frequency can compensate for even a very significant lack of data, which is common for many real-world systems where data collection is expensive. In this example, we only require half as much data to achieve the same performance by increasing the control frequency from 18 to 24 Hz, which is a 33% increase. With these insights, I'd like to conclude my talk. We have developed a framework that allows us to use the control frequency as a design parameter and to study its impact for learning-based sample data control of uncertain systems. We could show that there is a trade-off between the control frequency and the amount of data. Increasing the frequency can make up for even a very significant lack of data and vice versa. In future work, we aim to extend this framework to online learning and also to adapting the control frequency online if the model changes. And we would also like to consider more difficult tasks than set point stabilization, such as trajectory tracking. Thank you very much for your interest.